Hey, welcome back. So now we're going to handle errors of analysis, things you're doing wrong. We spent a bit of time talking about inferential statistics and p-values during this quarter. And it's important to realize that just because some number says, hey, this is statistically significant, doesn't mean we should care. Right? So, for instance, let's think about it. We have a cure for baldness. Okay? And the company that's bringing out this cure for baldness is getting a lot of investor money because they've said, hey, we can show, in a statistically significant way that our magic potion makes your hair grow back. Okay, great. Does it grow back like peach fuzz? Or does it grow back so that you've got to go to the barber and get the top trimmed? Okay, so something may be statistically significant without being practically relevant. And it's important to distinguish between these things. And there are measures of practical relevance. There are measures of effect size. I have not covered those at all, but then again, to be honest, the coverage of inferential statistics in this course is pretty small because you're not quite ready yet when you're taking this course. But in the future, as you do more statistics, you will learn about effect size measurements and understand that it's important to realize not just is it statistically significant, but is it actually useful? We also already talked about Anscombe's quartet, which is 4 different sets of data points, which, they have all the same statistics, every single one of these data sets. Their mean is the same, their variance is the same, their correlation between x and y is the same. You fit a line to them, you get the same line. But they're very different data sets. Why is this relevant? Well, this is a case where we are making assumptions. Every time you do a statistical analysis, there is an implicit assumption. There is something going on in the background where the math that forms the analysis is assuming that we have some set of characteristics to these numbers coming in. And if you break those characteristics, if your data is not of the form that's assumed, then the analysis is completely bogus. So it's your responsibility as a data scientist to understand what the assumptions are, what the math is telling you, and understand that, if you can't identify cases you should not apply an analysis, then you're not a good data scientist. Every analysis you ever do, you should be able to articulate, when should I not do this? Please always keep that in mind as you're learning things in the future. Okay, here's another very typical way to get confused when doing an analysis. So in '73, UC Berkeley was sued for sex discrimination, and the numbers looked bad, right? The graduate school had accepted 44% males and only 35% females. So this looks like a clear-cut case of, some sort of anti-women sort of bias. Well, first off, before we get into this technical details, let me just first say this is not some way to say there is no bias against women, because there is, right? What this whole analysis is showing is that sometimes when looking for things that you know to be there, you make mistakes and you misunderstand a situation. So here's the paradox that we are faced with. It was not true. If you look at, in this case, the men and women, right? So men here, women here, and you look at the groupings, then you see that the numbers for men are much, much higher. It looks exactly like what we were saying earlier, that men are admitted and women are less admitted. Okay, but what if we break this up over the departments instead? So there's departments of, whatever, mathematics, and physics, and literature, and whatever else we have in our school. So when you do that, if the data is pooled properly, there is actually a small but statistically significant bias in favor of women. So let's take those numbers and redistribute them. So what we see is that in some disciplines which were highly selective, like F, okay, there were way more women than men. Okay, so this discipline is just highly selective. Sorry, I said that wrong. This discipline is just highly selective, and it actually, this one's roughly equal in terms of the numbers of gender, and you can see there's no bias there, right? This one likewise, more of them are admitted, and the admissions look a little bit more biased towards women in that case. Okay, so each one of these subgroups looks relatively even, with the exception of C, where there are way more women applicants than male applicants. And B, there are way more, just tons and tons more male applicants than female. Right, so what's happening here? There are fewer women applying to the more permissive kinds of departments, right? And more men are applying to highly selective departments. So that produces a solution. Sorry, I have that exactly backwards. Yay for late nights. More women are applying to highly selective situations. So the vast majority of women are in these cases over here, and some of them are highly selective. Whereas the vast majority of men, you have a lot of them over here, and this admission process is much less selective than these ones over here. So it just turns out that it's a confound between the department and the gender. So when you do it, right? So let's say these are the data from Simpson's Paradox. Okay? If you were going to draw a line of regression through all of the data, you'd probably draw this line here. Right? It doesn't look like a great fit, but that's the fit you're going to get. However, if you realize that what exists here are subgroups, then you end up finding a completely different relationship when you fit on the subgroups. Okay. So we can make mistakes with data. We know that, right? But maybe just as important as not understanding how we're analyzing the data or how to analyze the data properly is when those cases when we don't actually come in with a hypothesis at all. Okay? In most scientific, I would say in almost all scientific endeavors, and in many just analytic ones, you want to come in to the process with some idea of what you expect to find, and preferably a very formally defined hypothesis. Because if you don't define what you're expecting to find, then it's easy to just shoot your pistol and look at the dots and claim after the fact where you were aiming for, which of course you may not have been. Maybe you're fooling yourself. Maybe you're lying. So this is called the Texas Sharpshooter, and we also call it harking, hypothesizing after results are known. HARK is the lovely acronym. So this kind of thing is very doubtful science, and it also makes for doubtful data science. So before you come in to do an analysis, you want to know what you expect to find, because you're setting up your analysis based upon your hypotheses. So if you just kind of dumpster dive in the data, you know that you will eventually find some lovely false positives that you can publish, right? And the thing is that publications are known to have a bias towards things that make a significance level, right? So nobody tends to publish things where the p-value is 0.34, right? If the p-value is 0.34, that says there's a 34% chance that the results that we're seeing here, or something even weirder, are happening by chance. And that actually condition A and condition B that we're testing here, they're exactly the same condition. It's just that we got different numbers because of different rolls of the dice. And a 34% chance that something is, truly the null hypothesis, that there's actually the same deal in both conditions, right? 34% is too high for most people to accept. So we'll say, okay, that was a failed study. I'm going to stick the study into the file drawer and leave it there forever and never pull it out. So this is a problem. This is a problem because science and data analysis need the data. We need to know what doesn't work as much as we need to know what does work. And if you just publish only the things that randomly make significance, you are setting yourself up for some lovely false positives. For that, green jelly beans cause cancer XKCD cartoon that I put up once. So the problem here is that what we need to do is we all need to make sure that we publish results even when the results are bad. Okay? We need to communicate, oh, this didn't work. We need to show the world that here is some data I collected which don't show anything interesting about how Donald Trump became president. Okay? That data needs to be out there, because if it's not out there, then somebody else is going to end up doing the same bad thing and repeating your mistakes. It needs to be out there so that we can know and have confidence that when you do publish something, that it isn't a false positive. Wait, how does that work? If I know that you've put out a bunch of bad results, where you've published things and put them on your blog or in a white paper or an archive preprint, right? And you've shown me all the things that go wrong that never did anything, why should I believe you? Right? Clearly you're a bad scientist. You're a bad analyst. Dun, dun, dun. No. I would believe somebody more if they publish their bad data. Why? Because two things. One, we know that you are a good scientist. You're following good, rigorous methods and reporting even the bad stuff. And two, by reporting the bad stuff, I have confidence. I can look at your overall hit rate. I can look at your overall hit rate and see, is this likely a false positive? How does that work? Well, this is a lovely figure that comes from using a machine learning algorithm to do some natural language processing and look through every single published bit of biological data that has been thrown through this Medline system. And it looks for the results of statistical tests. Okay? And what we would expect, testing everything in the world, is we would expect some sort of normal distribution. We would expect that some results are true, and that we therefore end up, looking at results out here and out here as things that are surprising new science findings that turn out to be true, right? But we also expect a bunch of the results to be in this range. We expect them to be meh. There's no relationship between hamburger consumption and the number of car accidents in Idaho. Okay, so there's We expect most things to be non-significant, to be in here, where this z is, when you get out to a certain point, you get out past 1.96, then you probably are in the level of significance. But what we see here is that, in fact, in the scientific literature, in all of the things ever published in biological science, basically between the 70s and the current time, there is a great, huge chunk of missing stuff, the dark matter of statistics, right? So these missing values we expect to be there. We expect to know that most things we test aren't true relationships. There is no relationship between the number of gummy bears in your couch's cracks and the federal income tax bracket that you're in. Okay? Just doesn't hold true. So we expect most things in that middle. So this missing dark matter of statistics is in fact exactly the same as a survivorship bias we talked about a little bit ago, right? We keep seeing all the dots. We keep seeing all the places where a scientific study can be hit by gunfire and survive. But what we care about is maybe the other thing. We care about all the things that are false. We want to know what things actually are not relevant for us in the future. Where is science going to die if it's hit by the gunfire? It's a very useful thing to know, and sadly, we don't really have data on it until people start to pre-register and put out even negative results. Okay, a last kind of way I want to cover with analysis that fails is when people don't know what they're doing. Right? When you just pick up an analysis tool and you have no effing clue what you're doing with it. So what happened here? This little news story. One of the standard ways to decide if there is racial bias in policing is to look if there's a difference about people who are stopped in their cars during the daytime versus the night. So at night, the officer can't see into the car necessarily very well. The officer may not be able to see the race of somebody inside. So if daytime stops for dark-skinned people are a much higher percentage of the total stops made than nighttime stops. If the percentage of dark-skinned people stopped gets close to their actual percentage in the population, and in the day it's 20% higher, then that is evidence of racial bias. The daytime stops, the cops can see who's in the car, and they could be pulling them over for driving while black, as they say. All right? So this is called the veil of darkness test, testing daytime versus nighttime stop rates to look for racial bias. So San Diego County Sheriff reported a veil of darkness thing. They said, hey, according to the veil of darkness test, we don't have racial bias in San Diego Sheriff's Department. They misunderstood some very important things. So what they actually tested was 5 to 9 p.m. versus all other times. So 5 to 9 p.m. is not all darkness hours. And depending upon the time of year, 5 p.m. is not necessarily even very dark, or any dark, right? So testing a couple of hours that are in the twilight most of the year versus all other times, which would also include the night shift, not such a good idea if what you're trying to test for is racial bias. So somebody who did this analysis, there are two interpretations. The charitable one is they just picked up a tool they didn't understand and they broke it. The less charitable one is that they knew exactly what they were doing and they were covering up something, right? So either way, you lose confidence in the analyst if you see something like that. You think they're either incompetent or malicious. So it's very important that you in your data science career make sure that you understand the tools that you are using and know when they can be applied and how they can be applied. Because if you don't, you will end up looking like this analyst, right? Nobody will trust. Okay, so I'm going to take another little short break and we'll come back with more. See you soon.